Forgot I had muted myself. How are you all doing this morning?
Doing well. How are you?
I'm good.
I took the FE finally yesterday, so that was something.
They're giving it now. I think they had put off giving it for a bit because of the pandemic and all that jazz.
Yeah, I was either gonna have to take it in the summer and drive the 6 hours to Dallas, or do it last week, which was finally when they opened Pearson over here in Shreveport.
Oh, cool deal. All right. Let's see. So I believe when we left off, we had just begun talking about parasitic diodes before my computer spazzed out. So let's continue from there. So when an N well is fabricated, in a P substrate, a PN junction occurs at the interface. So we have a simple situation like this. Here's our N well. The N well serves as the cathode, and the P well serves as the anode. So in CMOS circuits, the substrate is usually tied to ground. Which helps to keep the parasitic diode in the reverse bias region. Just a second to shut down my email client so I don't get spammed during class. All right. So as long as the voltage that's applied to the N well is greater than 0, typically speaking, everything is okay. So in your previous solid state courses, you may recall that a reverse biased PM junction forms a capacitor. A forward biased PN junction does too technically, but they're much less frequent. All right, so a shoddy drawing of this will be something like this. So let's put the junction there in the middle. So we have on the P side, that looks terrible. Of the junction, we have poles. And closer to the junction itself, we have ionized acceptor atoms, right? So they gave up their hole, so that's why they're negatively charged. On the N side of the region, of the junction, we have electrons. Then we have donor atoms that have given up their free electron, and so that's why we have positively charged ions. So this is what's going on. And this region in which there are no free charge carriers is what's called a depletion region. And we can control the depletion region width by applying a bias voltage. The more negatively charged so the more negative the voltage that we apply across the PN junction, the depletion region gets larger and larger and larger, which in turn causes the capacitance to decrease and decrease and decrease. And it's because we have a parallel plate capacitor effectively, where the plates are here at this interface. I can't stop being difficult. Between the ionized atoms and their free charge carriers. So it's a simple parallel plate capacitor. When we bias it more negatively, the plates get farther apart, and as hopefully you all remember from your basic E&M classes, the capacitance of a parallel plate capacitor is epsilon A, which is the cross-sectional area of the plate, divided by D. So as D gets larger, D is the spacing between the plates, we see that the capacitance goes down. All right. So in this particular capacitor, the capacitance is modeled as CJ, which stands for junction capacitance, is CJ naught, which is the unbiased junction capacitance, divided by a factor of 1 minus VD, which is the biasing voltage, divided by VBI, which is what's called the built-in voltage of the junction raised to the mth power, where M is the grading coefficient. So just to be clear, CJ naught, unbiased junction capacitance, VBI, built-in voltage, M is the grading coefficient. CJ naught is epsilon A multiplied by Q over 2 epsilon VBI times the product of the donor concentrations or the impurity concentrations divided by the sum of the impurity concentrations. And then we take the square root, where epsilon is the permittivity. And for silicon, it is 11.8 epsilon naught, where epsilon naught is the permittivity of free space, is a constant 8.854 times 10 to the minus 12 farads per meters. But you can look that up easily on Wikipedia and all that kind of stuff and not have any issue with the number being wrong. Q is simply the charge of a proton, 1.6 times 10 to the negative 19 coulombs. Lastly, we have the equation for our built-in voltage, where VBI is Boltzmann's constant, KB multiplied by the temperature, divided by the charge, multiplied by the natural log of the product of the impurity concentrations divided by the intrinsic electron concentration squared. So Kv, Boltzmann's constant, (1.381) times 10 to the negative 23 electron volts per degree Kelvin. I is the intrinsic concentration, which some textbooks have different values, so the one that we're going to use specifically is 1.45 times 10 to the 10. Free electrons per cubic centimeter. So some textbooks have this as low, excuse me, as 1.0 times 10 to the 10. I've seen others as high as 2. The textbook that I like the most actually has it as 1.1, but the textbook for this class uses 1.45, so that's what we'll do just to make things legit. All right, so let's talk about grading coefficients real quick. So we have an option of a step graded junction. Formed by an abrupt change from acceptor ions on the P side to donor ions on the inside. Have a grading coefficient of 1/2. So as effectively as I've drawn it up here, where abruptly it shifts from completely ionized acceptor atoms to completely ionized donor atoms, that would be an example of a step graded junction. Think of it kind of as like if you had an N-type piece of semiconductor and a P-type piece of semiconductor, and you were able to fuse the edges together, that would be a step junction. So they don't really occur an awful lot practically. The other option is a linearly graded junction. And these occur where the change from acceptor to donor atoms varies linearly. This is much more likely to occur because of the annealing process that all CMOS based excuse me, devices go through towards the end of their fabrication. It causes diffusion of the dopants, and so excuse me, we see that even if we've done ion implantation to force the junction to be close to step as we can make it, when that diffusion occurs, there's a region where things kind of mix. And these guys have a grading coefficient of 1/3. Alrighty, so let's take this knowledge and just a second, I need to take my inhaler. Working example problem. I apologize for that interruption. Let's say that we want to determine the depletion capacitance of an N-well P-substrate diode with dimensions of 100 lambda. So 100 times the scaling factor of our process in one direction and 100 times the scaling factor of our process in the other direction. And let's say it's a C5 process. Therefore, lambda is equal to 300 nanometers. Given that the substrate doping is 10 to the 16 per cubic centimeter, and the well doping is 10 to the 17 atoms per cubic centimeter. Measured zero bias depletion capacitance of the junction is 100 attofarads per micron squared. And that's one thing that's actually kind of interesting about the numbers that we're going to be, excuse me, wind up using here. Whenever we talk about these capacitances, we really mean the capacitance per square, actually. But it's not the same as per square that we saw with resistances, because we know that the area of the plates vastly influences the capacitance values. And so it's not going to be uncommon for us to see units of actual capacitance per square micron for some things, particularly what we will call area capacitances. And then we're also going to have fringe capacitances, which we'll talk about a little bit later, where we're going to see that those are measured in capacitance or farads per micron, so not squared. And it's because the thickness value for the fringe capacitance is usually fixed, so it's built into the unit. Anyway, let's get back here. And the grading coefficient is M is equal to 1/3. Assume that the depth of the well is 3 microns. Okay. So this problem was actually pretty straightforward, but we would need to recognize one very important thing, okay? So if we look at a picture of an N-well substrate junction, where here is our N-well, we have an obvious capacitor formed between the bottom of the well and the substrate. But what you may not obviously see is that there's also going to be, excuse me, what's called a sidewall capacitance. So this is the bottom capacitance, and this is the sidewall capacitance. And these two guys are connected in parallel, right? Because they share one node in the N-well and the other node in the substrate. But they're both going to contribute to the overall depletion capacitance of the parasitic diode. So that means that overall, we are going to see that the junction capacitance is going to be what we'll see, CJ0B for bottom, 1 minus over VBI to the M plus CJ0S. So the unbiased junction capacitance of the sidewall capacitor, 1 minus VD over VBI. Yeah. So to determine the zero bias depletion capacitance for the bottom, that's going to be simply CJ0 times what? Does anybody have any ideas? So recall that CJ0 is the capacitance of the 100 attofarads per micron. So this guy has units of AF per micron squared. And this guy has units of farads or attofarads or something like that. So what area are we supposed to be multiplying this guy by?
The N-well P subdimensions, I think.
Right, so it's going to be the 100 lambda by 100 lambda bit, right? So that's going to be 100 squared times, or let's let's be more explicit here. The bottom area times our scaling factor squared. And so when we put in numbers, this is going to become 100 attofarads per, or actually let's, 100 times 10 to the minus 18 farads per micron squared times 100 squared, right? Because it's a 100 by 100. And then we also have our lambda, which is 300 times 10 to the minus 9. Or actually, 300, come on, pen. So if it's 300 nanometers, it's 300 times 10 to the, stupid pen thing, 3 microns, right? So I'm trying to get my units legit here. And if we multiply all of this out, we come up with 90 femtofarads. For the sidewall zero bias depletion capacitance, we're going to have a similar expression, Cj naught. But what area are we going to be multiplying by here? So from a top-down view, we have, here's our N well, and the dimensions here are 100 lambda, and the dimensions over here are also 100 lambda, right? So our area is going to be the perimeter of our N well multiplied by the depth of our N well. Does that make sense? So we're following this guy right here all the way around the perimeter, and then we're also including the depth because that gives us area. So that's the total surface area of the N well, minus the bottom. So we have in here, well perimeter, well depth, lambda squared. Actually, hold on. Only one lambda. The reason why it's not lambda squared is because our well depth is given to us in the actual dimensions, right? So if we squared it, we'd actually have units of microns cubed. Alrighty, so if we substitute in our numbers, 100 times 10 to the minus 18 farads per micron squared. Sorry, no squared there. The well perimeter is going to be 400 lambda. So lambda is 300 times 10 to the 3 microns. And then lastly, we have our well depth, which we were told was 3 microns. And we find that this gives us a value of 36 femtofarads. So we have Cj naught B and Cj naught S defined. So now let's figure out what our built-in voltage is. So VBI is going to be KBT over Q. So actually, let's revisit that really quick because I forgot to mention something. So at room temperature of 300 degrees Kelvin, this is approximately equal to 25.9, so let's call it 26 millivolts at 300K. Okay. So let's assume that value. Times the natural log of the acceptor concentration, which is what our well doping is, times our donor concentration, which is our, the acceptor concentration is the substrate, the donor concentration is the well, and then divided by 1.45 times 10 to the 10 quantity squared. We do the math here, we get 759 millivolts. And so we can see that our junction capacitance as a function of VD our biasing voltage is 126 femtofarads. So that's just this guy and this guy added together, divided by 1 minus VD divided by 0.759 volts. And because we were told we have a grading factor of 1/3, there we go. So we can see now how our junction capacitance is going to change as a function of bias voltage based on the geometry of this system. All right, so this is our last bit of topic on wells. That was terrible. RC delay through an N well. Okay. So we have seen that N wells have both a resistive and capacitive characteristic. It shouldn't be a surprise. Shouldn't be surprising, I guess, either way we want to put it, that N wells actually form an RC network. All right. This is where our input voltage is the in. There's going to be resistance to our output. There we go. And we know that we're going to form capacitive network as well. And I'm distributing it like so, because effectively what it does is it forms a type of transmission line, and we'll talk about that momentarily. All of these are tied together to our substrate, which is typically grounded. And all of those capacitors are the parts of the depletion capacitance that we discussed previously. So we can simplify our drawing a bit. So, excuse me. So for a simple RC circuit, and this is going way back to circuits 1 material. So when we have something like this, we apply a step function to it, which is like flipping a switch. We saw here's time, here's the voltage. So our input signal, which I'll draw in blue for the sake of argument, if it was like this, so it just stepped up to what we'll call V pulse at t is equal to 0. This guy is Vn. Our output voltage, which will be in red, had an exponential response, like so. And mathematically, we can describe that exponential response as V out as a function of time was our pulse magnitude times 1 minus e to the negative t divided by RC. Okay. So we're going to define, based on this relationship, a few parameters of interest for us in the performance of a CMOS integrated circuit. All right. So the first thing that we're going to do is we're going to define what's called the delay time. As time it takes the output to reach %50 of the input signal level. So CMOS design engineers effectively are defining a different time constant than what we used in class and what's practically used in, say, the power industry and stuff like that. So from this definition, we can see that 0.5 V pulse is equal, that's our desired output voltage, is equal to V pulse times 1 minus e to the negative td, our delay time, divided by RC. And we can solve this guy and find that our delay time, td, is simply negative RC times the natural log of 0.5, which is approximately 0.7 RC. Another figure of merit is the rise time. So we will define the rise time as the time it takes for the output to go from 10% to 90% of the final voltage level, which is V pulse. So we know that 0.1 V pulse is equal to V pulse times 1 minus e to the negative t 10% divided by RC, which tells us that t 10% is going to be negative RC natural log of 0.9. Similarly, 0.9 V pulse is equal to V pulse 1 minus e to the negative t 90% over RC. So from this, t 90% is negative RC times a natural log of 0.1. And our rise time, TR, our rise time, TR, is simply T 90% minus T 10%, which is negative RC natural log 0.1 minus natural log 0.9, which is approximately 2.2 times RC. All right, so these are the rise times and delay times of a simple RC circuit, all right? But our N-well RC circuit, excuse me, is a distributed RC circuit, like an RC transmission line. So I guess I'll come down here. So here is N. Here we have R square. Let's call this node point A. And here we'll have a particular capacitance. Here's another R squared. This won't look like squares very much. Here's B. Here's another capacitance. And so forth until we hit node N. Where we find our output voltage with respect to ground, which would just be the voltage drop over that last capacitor. So because we have a distributed network like this, it means that there's going to be a particular amount of delay to node A, and then node B, and node C, etc. So for this distributed case, the delay to node A is, let's call it TDA, is just the 0.7 R squared C squared, which is exactly what we would expect based on our simple model, all right? But now we have to also account for the delay to node, for the signal to propagate to node B is TDB is 0.7 R squared C squared plus 2 R squared C squared, right? So it takes extra time for the signal to propagate all the way to node B. Similarly, the delay to node C is going to be 0.7 R squared C squared plus twice R squared C squared plus 3 R squared C squared, because we have to get to the third node, and it just increases like that. So from this, the delay to node N, the output, is TDN 0.7 R squared C squared 1 plus 2 plus 3 plus all the way out to N, which we can do in summation notation. And this is simply a geometric series, I believe it's what it's called. And so we can simplify it to 0.7 R squared C squared multiplied by 1/2 of N times N plus 1. That's what the sum from 1 to N is. Mathematically equivalent to, or 0.35 R square C square N times N plus 1. Using a similar derivation, the rise time to node N is 1.1 R square C square N times N plus 1. All right, so the last thing we have to do now, for this section anyway, is to work a quick example problem, and then we're going to take maybe a 5-minute break, and then we'll move on to metal layers. So let's estimate the delay time through a 250 kilo ohm resistor made using an N well. With a width of 10 lambda and a length of 500 lambda. Assume the capacitance of a 10 lambda by 10 lambda square of N well to substrate is 5 femtofarads. So we're trying to find the delay time, so we know that it should be the overall delay time, so let's just call it N, should be 0.35 R squared C squared N times N plus 1. We know what C square is. But we don't know what N or R square is. So how are we going to figure out what either of those quantities are?
Using the equation from like 2 lectures ago or a lecture ago.
Okay.
There it is, the R squared times length over W has to equal resistance.
All right, so we know the length times width relation. Okay, so you're saying that the overall resistance R is R squared times length over width, right?
Yes.
Okay, so that means that R squared is R and come on, times width over length. So that means we're going to have 250 kiloohms times the width, which is 10 lambda, divided by the length, which is 500 lambda. So it's 250 divided by 50 is 5 kiloohms. All right, seems legit. So how many, what's N? How many squares are there?
Just the one, I think. Or no. Oh, the squares come from the
Equal dimensions of the resistance, right?
right.
So a square is a 10 by 10 section. So how many 10 by 10 sections are in something that's 10 by 500?
I think 5, right?
50. Right, it's just going to be the length divided by the width. So 50 over 10, or excuse me, 500 over 10 is 50. Right, and we know that the smaller dimension is the one that's going to be on the bottom in order to make squares, right? So N is 50. So from this, TDN is going to be 0.35 times 5 kiloohms times 5 femtofarads times 50 times 51, and I believe this comes out to 22 nanoseconds. So that's the delay time of the signal entering our distributed network and then coming out the other side. In an analog CMOS integrated circuit, that delay time may not be a particularly big deal, but it could be a very large problem for high-speed digital circuits, which is something that we're going to talk about a bit later. Alrighty, so let's take a brief break and come back at 9. I'm going to save this as it in the right folder.
Dr. Hartman, would you upload the note in the Moodle?
Sure, I can upload the notes. And
Okay.
I'm also, I'm recording these lectures, and this weekend I plan on uploading them to YouTube, and then putting from the YouTube channel to the class as well, so that you can have a copy of the notes that I'm taking down or giving to you guys, and also watch videos, since I sometimes talk about other things too. All right, so now that that is saved, let's see, edit, remove all the annotations, go back to the first page, and let's save this as chapter 3 notes. Okay, I'll be back in just a moment. things. So the next topic that we're going to deal with is the metal layer. All right. So in our process, layer called metal 3 is the topmost layer. So just as a very quick aside, from a top-down view, we might have something like this. Where the green still are N well. And I'll use orange for metal 3. So this is our top-down view. And then our cross-sectional view of this, let's see, here would be, make sure I give myself enough room. Here's the, so here's our substrate. There's the bottom. Here is our N well. Then we're going to have our field oxide layer, which is an insulation layer. We're going to have another insulation layer. This is where our polysilicon layers, which we'll learn about, I think, probably Tuesday, would go. Then we have a layer here, which is where metal 1 would be. Then we'll have a layer here, which is where metal 2 would be. And then lastly, we'll have a layer here of insulation, and then our metal 3. So let's metal, yeah. Our metal 3 layer will be put in this guy. And they're overlapping, so something like this. I guess technically there is one more thing on top, and it is an insulating layer, and it's actually critically important. And we'll talk about it, and it's what's called the overglass or passivation layer. But it's kind of tied into metal 3. I'm trying to draw it like so, to where there is an opening. So this topmost passivation layer is part of the metal 3 process. And it does something critically important. And what it does is it effectively holds down the thin film that of metal 3 so that it doesn't curl up and peel off the chip. Okay. We'll talk about it in a little bit more depth in a moment. So let's start with why we even have metal layers. All right. So metal layers are used send, not sing. So metal layers are used to send signals in CMOS ICs. So if we want to be able to apply a voltage to a transistor, we actually have to go through from metal 3 down to metal 2, down to metal 1, down to what's called an N+ implant in our N well to be able to apply a voltage. Like we do not have direct access to the N wells to create resistors or to send a signal to a resistor and all that kind of stuff. We have to go through the metal layers, and we cannot skip metal layers. So what I mean by that is you can't go from metal 3 directly down to metal 1 or to the N well. You have to go through all of the subsequent layers, and it's to maintain signal integrity, and also it winds up lowering the resistance of the path that the signals take, which is a good thing. So to get signals on or off a chip, bonding pads are used. And a bonding pad is simply a specific portion of the topmost metal layer. In this case, metal 3. So there are rules for bonding pads. So if you give me a moment, let me open up our design rule thing, which I need to get into Moodle to do that. Are you guys still seeing the PDF with the notes or the CMOS rules?
It's in the notes. Yeah, it's the note.
Let's see. Probably, I don't think that's the one I want. Okay, here we go. So these rules are actually for the overglass layer, but they define everything about how a bonding pad is formed. So the minimum bonding passivation opening is 60 lambda, and the minimum probe passivation opening is 20 lambda. So a bonding pad is minimum, well, actually, so there's going to be pad metal overlap of passivation as well, of 6. So the minimum dimensions for a bonding pad on the metal 3 layer are 72 microns by 72 microns. That's the absolute minimum. And then there's the square opening in the overglass layer that allows contact to the bonding pad. Now, there's also, you can use the topmost metal layer for probe openings, which is defined in 10.2. And we'll talk about it in a moment, but effectively, probes, their openings are smaller because we're not permanently soldering anything to it or anything like that, right? Probably some of you graduate students, if you haven't yet, you probably will soon have to use a micro probe array, which is effectively a needle with a wire in it that is connected to a stage that can move in the X, Y, and Z directions. And so you use that with a microscope to be able to troubleshoot integrated circuits and all that kind of stuff. So you don't need a permanent connection to it. You just need a temporary connection. And so that allows you to actually have a smaller opening in your overglass layer. And there are a couple other rules: minimum pad spacing to an unrelated metal, and minimum pad spacing to active poly or poly 2, which since our bonding pads are going to be on the metal 3 layer, rule 10.5 kind of doesn't even apply to us. All right. So let's go back to our notes. So, as discussed previously, a moment ago, really. For a bonding pad, the minimum overglass opening is 60 microns, and this was rule 10.1. The pad metal overlap of the overglass is minimum is 6 microns. This is rule 10.3. So this means that the minimum size of a bonding pad is 60 microns plus twice 6 microns, because it needs to overlap on all sides, is 72 microns. So we would see from a top-down view something like this. like so. So this is the absolute minimum size needed to be able to connect a wire to a chip in the C5 process. For a probe, the minimum overglass opening is 20 microns. And the pad metal overlap overglass is still 6 microns. And so the minimum size of a probe pad microns plus 6, sorry, 2 times 6 microns is 32 microns. And I won't draw a picture because it's going to be effectively the exact same thing but smaller. A note, you must include overglass openings. For bonding pads and probe pads. Why? Anybody have any idea why you have to have an opening?
So you can actually connect with the probe or whatever the heck you're putting in there.
Exactly right. If you don't, you have a very hard layer of insulating material over your bonding or probe pad, whose job is to not conduct electrically. So if you don't remember to include the openings, you don't have any way to put a signal on or get a signal off of the chip. That's looks like 2 E's and 2 C's. A, C, C. All right. So now let's talk about, get myself organized here. The capacitances in CMOS metal layers, okay? And specifically, we'll talk about for a C5 process. So I'm going to draw a quick cross-sectional view picture with multiple metal layers so that we can see things. All right, so let's put down here as the top of our substrate, and down here as the bottom of our substrate. So the size of some things. So this is what oxide layer. It's what isolates some transistors from other transistors, like when we don't want them to have a crosstalk or communication or anything like that. Then the next layer is the layer that we would consider our polysilicon layer. And so in the polysilicon layer, we might have poly 1, which is what we use. Actually, let me draw it lower because it would be directly on top of the field oxide. Poly 1, which is what we traditionally use for the gates of transistors. And then there's also a second poly layer that we would be embedded physically higher up in the poly layer. So this is poly 2. And what the poly 2 layer is for, and we'll talk about this in great detail again, I think on Tuesday. So if the field oxide, or effectively, you can make transistors with the poly 2 acting as a gate, and they are going to have a significantly different turn-on voltage because the thickness of the oxide between the polysilicon layer and the channel of the transistor is much, much larger. So you can actually develop 2 different transistor technologies using a 2-poly process. A much more common use of the second polysilicon layer is the formation of what are called poly-to-poly capacitors, because the poly 1 and poly 2 can both be made conductive, and they are physically closer than any 2 other conducting materials in the entire CMOS integrated circuit process. So that's, typically use the poly layers to make very large capacitors because the distance between the layers, D, is very, very small. All right, above the poly layer, we have our metal 1 layer, which I'm going to put in I'm just going to arbitrarily make it large like this. So the metal 1 layer is the first of the metal layers. And if we wanted to connect from, say, metal 1 to poly 1, we would use what's called a via. So vias are used to make contact between different layers. They're little tungsten plugs. They have a finite resistance. Again, we'll talk about them in great detail in a little bit. Now, the physical dimensions of metal 1, the metal 1 layer, is smaller than that of the metal 2 layer. So metal 1 is actually the thinnest layer of metal, and so it has the largest sheet resistance. Then we have the metal 2 layer. I think that one is in purple. and we could connect down to metal 1 with a via if we so chose. And then a real thick layer, which actually that looks the same as the thickness of the metal 2. So let's make it even bigger. Would be our metal 3 layer. Like so. And then finally, we have our passivation layer. Like so. So, just because I didn't draw it, we may also have, so the capacitances that we can see, particularly with the metal layers, be metal 3 to metal 2. Metal 2 to metal 1. Metal 1 to poly 2. Metal 1 to poly 1. And if we didn't have a poly layer, I think we can also see a metal 1 to N-well and a metal 1 to substrate, right? Given information on, say, metal 3 to substrate, even though we could actually form a capacitance using that. And so the reason why I say that is if we tried to form well, actually, hold on just a second. No, that's not what I'm looking for. All right. So this actually might be a better thing to look. Let me share this. So like as part of last year's test, and I'll do the exact same thing for you guys, I gave a table. And this table is from a CMOS, a C5 process fabrication run. And so you can see that the that's not what I wanted. Plus layers, which are implants, which we'll talk about a little bit later, can form a capacitance with the substrate. Over here, okay, so they do have measurements for metal 1 to substrate, metal 2 to substrate, metal 3 to substrate, N-weld to substrate. Then active regions, which we haven't talked about yet, metal 1 to poly 1 and poly 2, metal 2 to poly, metal 3 to poly, and then we also have, you know, metal 2 to metal 1, metal 3 directly to metal 1, and then metal 3 to metal 2, like that. So these are all area capacitances. We have information on all of those. And then we also have fringe capacitances, okay? So we have a parallel plate capacitor. Like so, let's say that this is our metal 3 layer, and this is our metal 2 layer. There's going to be E field directed down like so, that's well behaved and is going to largely do what we expect it to do. But there's also, because these are finite metal plates, we're also going to see that we have fringe capacitances that we have to deal with. And the only way that we can know what these are is literally by experimentally measuring them, okay? The mathematics does not work well for finding out what the fringe capacitances and all that kind of stuff are going to be. So we only can rely on what our experiments tell us they are. So we are going to have to pay attention to parasitic capacitances formed by the different metal layers and all that kind of stuff, an awful lot. So I believe, let me look through this real quick. I'm not going to give you guys the same test, just so you know. Is this the, did I not ask a question about capacitances on this one? I guess I did not. All right, well, then I'm definitely going to ask you guys a good beefy capacitance question on your exam, your take-home exam for sure. All right, let's jump back over to the notes. And I'll upload that table on Moodle. Estimate the capacitance between a bond pad having units of 75 micron by 75 micron, so slightly oversized from the minimum, and the substrate. And from that table, we know that C area for metal 3 to the substrate is 8 attofarads per micron squared. And our fringe capacitance between the metal 3 and the sub is, let's see, 26 attofarads per micron. Alrighty, so this actually should be pretty straightforward. the area capacitance, let's just call it C A, and it's going to be very similar to the bottom capacitance here, is going to be 8 attofarads per micron squared times the area of the plate, which is 75 microns quantity squared. Is fringe capacitance is going to be our value of 26 attofarads per micron multiplied by the perimeter of our pad, right? So that's going to be 4 times 75 is 300 micron. And so 26 times 300, 7.8 femtofarad. Total capacitance is then 52.8 femtofarad. Okay, so let's see. Talk now about the resistance metal layers for just a couple of minutes here. Alrighty. So a wire. I didn't. Super well. All right. So let's say that we had a wire, and it's going to be on our metal 3 layer because we already have some information about that, right? And our wire is 3 lambda in width, and let's say it's 100 lambda in length. Sheet resistance of our metal layer is going to be 0.1 ohms per square. So the metal 3 is going to have the best resistance. Metal 1 is going to have the worst sheet resistance, but they're all still going to be under 1 ohm per square because they're so much more conductive than dope substrate and all that kind of jazz. So we could easily see that the resistance of this wire is going to be simply R squared times L over W, as it has been previously. 0.1 ohms per square multiplied by the length, which is 100 microns divided by this. .33 repeating ohms. So one thing that I want to point out here, the length of this wire is 100 lambda, right? L is 100 lambda is 100 times 300 microns. 30,000 microns, or 30 millimeters. So 30 millimeters, but it has a resistance of 3 ohms. So the resistance of the metal layers that we see in CMOS processes are actually significantly higher than what we would see if we were looking at the resistance of 30, AWG 22 wire, which is what we use a lot to build circuits in the classes here at Louisiana Tech. So it's very, very easy, and this is something, again, I keep saying, we're going to discuss this later, but it's very, very easy to cause what's called ground bounce and things like that, where effectively you're having a significant enough voltage drop over your section of wire that's connecting 2 points in a circuit to cause, say, your transistor to not actually be able to turn on. Could anybody think of a way to where you could eliminate resistance of a metal wire in a CMOS process? Like long straight wire right here. What could we do to make the resistance value smaller?
Add some sort of capacitance.
Well, it's going to have a capacitance associated with it anyway, and we're going to talk about that in a minute. But all of these things are based on the sheet resistance, right? Which is the resistance. In order to make this have a lower resistance, we need to effectively minimize the number of squares. So if we made it wider, so instead of it making it 3 lambda wide, we made it 6 lambda wide, we should see that the resistance cuts down by a factor of 1/2. So when you guys are doing your design portion of this class, you really need to think carefully about often using kind of wide, fat wires in order to minimize your ohmic losses between 2 different points in a circuit. That's going to help you with both heat dissipation and with minimizing the voltage losses in your system. I don't think we have quite enough time to talk about the capacitance and delay in a wire today, because we only have like 3 minutes left. So we'll pick up here on next Tuesday. I only have like 1.5 more pages of notes on the metal. It's pretty straightforward. Before we jump into some of the other layers, like the active layers and polysilicon layers and all that kind of jazz. So I will catch you guys all on Tuesday.
Have a good one.
You too.